Microsoft Paint?
Yes, you can share. You can share with your writings. Do you know how to share your screen or share your
Yes.
file? Okay, go ahead. Then you read. Then I read. Yes.
So here is the question. It's basically a combustion reaction. You don't need to know that though. And basically what it's asking for is to convert each molecule into basically a vector. So for instance, there are 3 carbons, 4 hydrogens, and 3 oxygens. So I wrote that as, and it also wants the P as an unknown coefficient. So I basically wrote that as P, so that's a scalar multiple, times 3 for carbon, 4 for hydrogen, and 3 for oxygen. Then over here we have Q times O2. So basically we don't have any carbons, so 0. We don't have any hydrogens, so 0. And we have 2 oxygens, so that's 2. And I basically did that with carbon dioxide and water. And that's my solution to part A. That's the equation in ordered triples. Then it asks to find the smallest positive integer solution. So in order to find that, I basically did the scalar multiplication and basically converted it into a system of equations. So I multiplied, then I added, then I converted to a system of equations. So basically we have 3p equals r, and 4p equals 2s, and so on. And after solving for all of that, which is right over here, not the prettiest work, but I found that essentially r equals 3p, s equals 2p, and q equals 2.5p. So I basically solved them all in terms of p, so that I could basically plug in an integer for p and get integers out of r, s, and q. So in this case, q is the only decimal or fraction, whatever you want to call it. So basically, if I multiply 2.5 by 2, I'm going to get 5. And so I basically set p to 2, and I solved that, and I have integer solutions for each unknown coefficient. And then it asks to draw it in space, and I kind of tried my best. It's still bad though, but because I solved by plugging in p, I consider that sort of as not part of the diagram. So I basically just did r right here, s, and q, and so we have r equals 6, s equals 4, and q equals 5 as a point in 3D space, and that point is right here.
Okay, let me see. What do you have to draw? Oh, just a solution. Okay, just a solution. All right. So let me ask you a couple of questions, Ryan. So serve as a review. Can you go up? Thank
Sure.
you. All right. So it's great, but I would like to hear more mathematical terms. So this question is application of the mathematics, ideas, concepts. But I would like to hear next time to hear something about vectors. So basically, you are given 3 vectors here: C3, O3, O2. Those are vectors. O, right?
So
Oh no,
I think there are 4 vectors. 4 vectors
1,
with 3 components. Well,
3, 4.
some of them have 3
Yes.
components, some 2.
Okay, so if they have 2 components, we're just treating the third one. We can make them a 3 components. The third one just 0.
Right, right.
Right. Okay, great. So you have these given vectors and you have scalars. You mentioned the scalar multiplication. I love that. Right, because last class we know if we're given vectors, we can add them, we can subtract them, we can do scalar multiplication, we can do dot product, we can do cross product. Right. Okay, great. I just want to hear more mathematical terms. Anyone has any questions? All right, if no one has questions, that's done. That's Ryan. Thank you, Ryan.
Thank you.
Okay. Okay, next one is Yuri, Y-U-R-I-I. Okay.
Yes. Okay, let me share the screen.
Okay, so after that it will be Ivy, then Tanya, then Jesilia. I'm so sorry, I cannot pronounce your name right. Just teach me how to say your name right. Gregory, and Dayeli, Adam, and Jung Yi.
Okay. 1 second, it's up.
Okay. I'm going to shut my door. Okay, the following people, please get yourself ready. All right, so up.
So my question
Nice.
is 1.1.21. And the question is, do the points 2, 3, minus 4, 2, 1, minus 1, and 2, 7, minus 10 lie on the same line? So the first thing I do is just put the points in the, they don't have a, like, I call them, and to find the vectors AB, BC, and AC, and try to show that each of the vector is like just the linear combination of the other two. I find vector AB, like each vector actually, by
Hold on 1 second.
Oh, oops. Sorry.
Hold on 1 second. How do I
Yes.
say your name right?
Yuri.
Yuri. Okay. So you want to see from the linear combination point, or it's just a scalar multiplication of one another.
Yeah, more like scalar multiplication. Yeah.
Right, scalar. Right. So if they're collinear, which means if they fall on the same line, we can write one in terms of the scalar multiplication of another. Okay,
Yes,
go ahead.
Wrong language. Sorry. Yeah. So like I'm showing that the other two are just multiples, like scalar multiples of other vectors, one vector. So how I find vectors, a vector IB, I just subtract the components of vector B from vector A, get the result 0, minus 3, and BC.
ABC are points. ABC are points, right? When we subtract, right, 2 points component-wisely, we get a vector.
Yes.
Right,
exactly.
Connected those 2 points. Great. Yes. Okay.
So
good job. Keep going.
Yeah, I got 3 vectors. From 3 points, I got 2 vectors, A, B, B, C, and AC. But actually, it was sufficient to get only one and to show it. But I just in case, I found 3 vectors. And from the components of these vectors, we can see that vector BC is -3 times vector AB, and vector AC is -2 times vector AB, which means that these vectors, these vectors are collinear, and that means that they lie on the same line. That's it.
Great. Right. So AC is -2 multiplied by, so vector AC is multiplication of -2 of vector AB. BC is -3 multiplication of vector AB. Right. That tells they fall on the same line. Great. Anyone has any questions? Because this is review class. So when someone explains the question, just make sure you can do yourself, or you already did yourself. If not, if anywhere confusing, it's time to speak up, to ask questions. Anyone has any question? Adam, go ahead.
In the textbook, when we're doing homework, I did the ones that were highlighted, but not all parts of it were highlighted. If the number's highlighted, are we supposed to do every part of the question, or just like the letter that's highlighted?
You can pick at least 7. You have to do at least 7. You can pick any number you want, but at least 7 to 10. Does it make sense?
No, I mean like when there was like multiple parts to one question, like only like A would be highlighted or something, and so I only did like the part A. Were we supposed to do the entire question, like A, B, and C, or just the highlighted section of the question?
I think ideally you finish all the parts. Ideally you finish all the parts.
Oh, okay. Thank you.
Right. You're welcome. All right, great. Good job, guys. Let me see. Gabrielle is asking, I know the first homework is due next Monday, but can we still present on chapter 1 after Monday? Depends on which one, okay? Not the basic one. If the question is very interesting, yes. All right, so ideally, we don't want to present chapter 1 anymore. We can go further, not the section 1 anymore, right? We're still at chapter 1. Ideally, we pass section 1, we can go ahead to section 2, section 3. All right, next one, Ivy, then Tanya. Please get yourself ready, because
Alright, so I presenting question 11, and it's asking for the points on the y-axis, z-axis, x-z-axis, and the y-z-axis. So for the y-axis, y has to be a real number, and in this example, I just chose 1 for every single one to make it simpler. And x and z are 0. So this just makes the whole point just stay on the y-axis. And that's the same thing for the z-axis. So z is a real number this time, and x and y are zeros. So z will just lie on the z-axis. For the xz plane, xz are real numbers, so it's going to lie in between the x and z axis, like for example over here. And because since y isn't anything, it just stays 0, and there's a vector for it. And then for the yz plane, yz are the points with real numbers, and x is 0, and there's a vector for it.
good job. Okay, this is a simple question, but very important concept. So I hope everyone gets this, because later on we're going to use this idea. So what's xz? What is xz plane? Xz plane is exactly the same as when y equals 0. Right? If you look at your corner, you sit in the room, you look at the corner, you could think the floor is your xy plane, right? The z value is 0. You can look at one wall, you can think that's a yz plane, then x value is 0. Then xz plane means y value is 0. Right? So make sure we equalize those concepts. Great. Anyone has any question? All right, good job. Tanya? Ryan is asking, have all the other homeworks been pushed back to Monday as well? I'm gonna do one by one. Sometimes, you know, after, because I'm with my family now. They're anxious. They're just waiting for me to finish my lesson, then do stuff with me. So, you know, I will update one by one. Thank you, Ryan. Keep reminding me, okay? Keep reminding me. Thank you.
So I'm going to be doing question 17. So the question says that the line passing through -1, -1, -1, and 1, -1, 2. So how to use the set theoretics or vector notation or both to describe the points that lie in a given configuration. That's what the question's asking. So I was looking at it as to look at the line. So the equation of the line for a vector is LT equals A plus TV. So A is the position vector and T is the parameter. And then I created a vector by subtracting the two component y's of, so I did like the second point subtracted by the first point, and I created that vector 2, 0, 3. And then I just plugged in the numbers into the equation. So for LT, then it became LT equals -1, -1, -1. That was the position vector. And then plus T, the parameter, and then times that by the vector that I created. And then I just added it together, and then it could be -1 plus 2t, comma -1, comma -1 plus 3t. Or you can write it as in I times -1 plus 2t minus j plus k times -1 plus 3t. You can write it like either way.
Beautiful job. Because I remember last time I didn't get chance to talk about this line representation using the idea of vectors. So in the formula, we have two vectors. We have initial vector, we have the direction vector. So in this case, you can, right, you find initial vector. You set the V, you subtract the 2 points, then you get your initial vector. Then you subtract 2 points, you get your direction vector. Right? Then you just name one of the point as the initial vector. Think about it as a line segment come off from the origin. And the line representation in space. So the beauty of this is we can represent a line in any space, right? We used to use y equals mx plus 1 plus k, mx plus b, no, mx plus b, right? That's in two space. That's only a line on the plane. But now with vectors, we can go higher dimensions. We can go n dimensions, 3 dimensions, 4 dimensions. So y equals mx plus b is not good enough to represent the line in space. So what do? We use the vector idea. And in the formula, we have two vectors. I just want to emphasize on this. But thank you. This is Tanya, right? Thank you, Tanya. You are basically teaching the lesson. So we use L of t to represent line representation in terms of this t. Right? T you could think as a time. Right? You could think like intuitively, it's like a time. Then the first component you calculate is -1 plus 2t. Second component is -1, which is a constant. The third one is -1 plus 3t. So this is a vector in 3 space because we have 3 components. You can think of this as x component, y component, and z component, right? Or when we go to higher dimensions, when we talk about dimensions more than 3 dimensions, so we would use x1, x2, x1 for the first component, x2 for the second component, x3 for the third component, so on and so forth. So we can go up to n components or n dimensions or n directions. And then with vectors, because we work vectors in Euclidean space. What is a Euclidean space? That means each direction is perpendicular with all other directions, or each axis is perpendicular or form 90 degrees with all other axes. Right? Or another representation of component vectors is this. We use ijk, right? ijk. In that case, we add them. We use addition sign, right? This one minus j is at negative 1j. So this looks like a point representation. We have three components, right? We have open parentheses, the first component, second component, we use comma to separate them. Then we close parentheses. So this is one representation of vector. Looks like a representation of point. And indeed, we do treat them the same, because a point is a vector with the initial point is the origin. So this is the second one, second representation. We use ijk, but no more comma. Sometimes students get confused, still using comma here. No. When we use the first representation, we use comma to separate them. When we use ijk, remember ijk are three vectors, right? What is the negative 1 plus 2t here is a scalar. So this part is a scalar. So scalar multiplied by a vector. So I is a vector, j is a vector, k is a vector. So enough, I'm going to talk about the unit vectors. They are unit vectors, which means the magnitude of each one is 1. All right. So we have two representations. The first one looks like a point, and indeed we treat it as a point. And we use a comma to separate them. The second one we use ijk, three vectors, we add them. All right. If we use a comma to separate three vectors, that doesn't make sense. All right. Mathematics doesn't have this convention. So if we use ijk, make sure we use addition. Okay, anyone has any questions? All right, great. Let's keep going. So that's Tanya. So next one is Jazelia, then Gregory, then Dieli, Adam, Zhongyi. Jazelia, are you ready?
Yeah, I'm showing it now. 1 second.
Okay, teach me your name. How to see your name right?
Oh, you're saying it correctly.
I did. Okay, thank you.
So the section I wanted to present was chapter 1, section 1.3, question 1. And so our problem was to verify that interchanging the first two rows changes the sign of the determinant. So first and foremost,
Hold on 1 second. Yeah, hold on 1 second. So you're doing section 3 already.
Yeah.
You finished 1 and 2.
Mm-hmm.
Okay, so no question was interesting for you. All right, so let me explain a little bit to the whole class. So determinant, or maybe you can help me with this. So how is determinant defined?
I wouldn't know the exact definition. I'm more so I know how to calculate them.
Okay, so determinant is defined with a 2 by 2 matrix, right?
Mm-hmm.
Right. So when we have, or maybe I'll explain to everybody. Maybe what we will try, I will help you to try to explain to everybody. So now what we have here is a 3 by 3 matrix. If anyone has any question at any time, feel free to jump in. All right, you can speak up or you can type in the chat. All right, keep going.
So like she said, we could do a 2 by 2 matrix for determinant, which is a little easier than a 3 by 3 matrix. So the methods to solving a 3 by 3 matrix could be a little bit different. So some methods include patterns and inversions, block matrices.
Let me stop you. Okay, I'm sorry. I'm trying to be picky here because this is new to everybody. So I will be picky, okay? Sorry for that. So, okay, determinant is defined on 2 by 2 matrix. So with the 3 by 3 matrix, we have to find out how to use the definition of 2 by 2 matrix. Remember last class, we talked about a cross product. It's very similar to the idea of cross product. But a cross product is a vector. Remember, scalar product or dot product is a number, right? So, but cross product is a vector. But here we're trying to find a determinant of 3 by 3 matrix. Determinant is always a number, all right? But the idea is similar to the cross product. But here we're not doing IJK. We don't have IJK anymore, so we won't get a vector. We get a number because IJK, before in the cross product here are numbers. But we still use 2 by 2. Okay, determinant is defined on 2 by 2 matrix. So basically, Cecilia is going to show us how to find the determinant of 3 by 3 matrix by using the concept or the definition of 2 by 2 matrix. Okay, keep going.
So like the professor was saying, you could do it the method of kind of like the cross product, which would be Laplace. Personally for me, I like to use series, which is multiplying the diagonal entries, which is essentially what we do on a 2 by 2 matrix, but now we're expanding it a little bit so we could do a 3 by 3 matrix. So in order to verify basically the problem, we have to calculate the 3 by 3 matrix without changing the rows for the determinant, and then also calculate it with changing the first 2 rows. So the first thing I wanted to do here was basically first define what is series, which is multiplying diagonal entries. So using the example without changing the first 2 rows, the first thing you do in series method is you take the first 2 columns, which would be in this case vector 1, 3, 2, and 2, 0, 0, and you simply just place them to the right of our 3 by 3 matrix. And now what we're going to do here is, as I said, multiply the diagonal entries. So your first diagonal entry in this case would be 1, 0, 2, which is basically column 1, row 1, times column 2, row 2, times column 3, row 3. And that just gives us 0. And then we do the same again for the second diagonal entry, which is column 2, row 1, column 3, row 2, and then column 4, row 3, which we get 4. And we're starting to see kind of a pattern evolve. You're going to go through all of the first 3 columns, and you're going to do the last one now is column 3, row 1, column 4, row 2, column 5, row 3, which is going to give us 0. And we're going to put a plus sign in front of all of these numbers. And so now I kind of separated out my calculations just to explain it better. But now we're going to basically do the reverse. And by reverse, I mean instead of doing column 1, row 1, now we're going to start off with column 1, row 3. And we're going to multiply the other way. So column 1, row 3 times column 2, row 2 times column 3, row 1. And we get 0 again. Now we're going to do column 2, row 3. I mean column 2, row 3, yeah. Column 3, row 2, and then column 4, row 1, which gives us 0. And then our final multiplication we're going to do is column 3, row 3 times column 2 times column 4, row 2 times column 5, row 1, which gives us 12. And I'm sure you're noticing there's a negative sign in front of it. Basically, because we're multiplying the other way, you're always going to put a negative sign on these 3 calculations. And basically when I was saying column 1, row 1, for example, that is the actual formula. That long lengthy piece I just gave you is the formula to calculate the determinant using Sayers' method. However, just visualizing it when you do a couple of the problems, you'll understand it a little better. But now we want to find the actual determinant. So now the easy part comes, we're just going to add all these values together. So we do 0 plus 4 plus 0, which was my plus side. And then in the black, I did the negative side. So minus 0, minus 0, minus 12. So our determinant without changing the rows gives us negative 8. And then now because we know how to calculate series, doing the change makes this a lot easier. So now we're simply going to interchange our first two rows. So row 1, 2, 1 switches with 3, 0, 1. And then we repeat series again. So now we're taking the first two columns, which is vector 3, 1, 2, and 0, 2, 0, and we're placing it to the right once again. And again, we're going to multiply diagonally. So for our plus side, I'm doing 3 times 2 times 2, which gives us 12. Then 0 times 1 times 2, which gives us 0. Then 1 times 1 times 0, which gives us 0. And now we're going to switch to our negative side, which we have to remember to put the negative in front of all of our numbers. So we're doing 2 times 2 times 1, which gives us minus 4. 0 times 1 times 3, which is 0. And 2 times 1 times 0, which is 0. And then finally, we're just adding all our values together to get 12 plus 0 plus 0 minus 4 minus 0 minus 0 equals 8. And thus we verified that if we change the first two rows, we're going to change the sign of our determinant.
Okay, that sounds to me it's a lot of work. Let me see. This is it. Abdurrahman Muhammad. So do we individually know who presented which question? I have jotted down everyone's. Can we create a Google Sheet as a whole, accessible to everyone, where everyone can log in and choose a question of their choice? That's a beautiful idea. You know, when I was in US, I was able to do that, but I'm in China. You know what? A lot of Google, Facebook, and a lot of websites are censored, which means I don't have access to it. Yes, cannot access to it. I'm so sorry. I'm so sorry. So, but here I have a list. I write down everyone's. So for you, if you don't know, you can just go up to the chat to see, all right, to see. So I basically write down a piece of paper to remind myself. I'm so sorry, all right? I have Google Drive. Everything of mine is on Google Drive. I cannot access to it right now. You made one. You made one, right, for everybody to do it, because I'm not able to see it. But among you, you can share this file. Thank you, Muhammad. That's a good idea. All right, thank you, Jazila Leah. Next one, Gregory. We have to go. We only have 16 minutes now. We need to finish before 7:30. Next one would be Daniele, then Adam, then Joey. Oh, I cannot hear you. Somehow I cannot hear you, Gregory. Yeah, you can use them on yourselves. I guess he's logging back on. So while we're waiting for Gregory, can Daniele go ahead? Oh, Gregory is here.
Okay.
Oh, yes, I can hear you.
Okay, I was about to go, so it's okay.
Okay, sorry about that.
Oh, that's okay. That's okay. You know, we're
Okay.
giving. Yeah.
No problem. I'm gonna go ahead and share the screen, okay?
Thank you.
No problem. Okay. Can we see my screen?
I think yes, now.
Oh, okay, great. So I'll be presenting question 3 from section 1.1. It's kind of early on, but it's a okay question. So here's our question, and we're solving for these components here in this vector with the scalar multiple of 1/2. And so first, you notice it's a message in the chat. Anyway, so first you want to just notice that we have a linear combination of this vector here, and it's made up of these two vectors on the right-hand side of the equation. And you just want to note that you want to find these components that I labeled as x1, x2, and x3, which will be the question marks. And then so I just applied the scalar multiple to each one of the components, x1, x2, and x3, so you could simplify and then solve for each of them, right? And so next we're just going to find x1 by labeling 52, which is the first component of the first vector on the right side of the equation, added to 1/2 of x1. And that equals to our linear combination 8a. And I solve for x1 starting by multiplying everything by 2. So we can get rid of the 1/2. And then you just simplify for x1. And it's the same process for x2 and x3, which would be the other question marks. And I rewrite the equation so that, you could solve for everything. And you just verify that the original linear combination is actually equal to what you find. And upon solving, you do find that 8a, comma negative 2b, comma 13c is equal to itself. And that's about it.
Nice. Okay.
Great. Thanks.
Okay, nice. Thank you. Thanks.
Mm-hmm.
All right, next one. Dayeli.
All right, I'm gonna share my screen really
Okay. Is it Dayeli or Dayeli?
Dially.
Dayeli. Okay.
Yes.
Okay, thank you.
Can you guys see my screen?
Yes.
Oh, okay. Why is it not presenting? Let me do this again. Share. Okay. Can you guys see my work? I don't know if it's okay.
It's coming up. Yeah.
Okay, good. So I decided to present question from chapter 1, question 25 from 1.1. This question right here to show that there is no point in our x, y, and z plane, in that it satisfies the this function right here equal to 0, in that that is lying on this line given right here. If we recall the equation of lines of LT equals A plus TV, so we know that we're given this equations right here. So I decided to just distribute the t's, and I'm left with this x, y, and z function. So know our x, y, and z. So then the last step to do is to plug in to this function of our 2x minus 3y plus z minus 2 equals to 0 to check if our function lies on the line. And in the end, I was left with 7 does not equal to 0. And then I give a sort of like an explanation why that is. So in the end, I concluded that it does not lay on the plane.
Great. Good job. Anyone has any questions? All right, nice. So next one, Adam. After Adam is Joey. Adam, are you here?
Yeah, can I have a second to get it up, please?
Sure. Next time, please get ready ahead of time. Anyone has any questions? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So 9 students presented today, and the 17 of you, that means 17 of us, 16 of you. So that means 7 of you probably can present the next class tomorrow, okay? You don't have to present every time, because right? If we present it 10 times, you get full credits. Nice. Adam, I cannot hear you. I think you're muted.
Yeah, I'm trying. I've never used this before, so I'm not sure exactly how to like zoom in on the file.
Oh, I can do that. I can
Oh,
do
you
that. Don't.
can? Okay.
Right. But your file disappeared. You have to share
Yeah.
again.
Okay. I was gonna do number 1 because the questions I found interesting were already taken. Because I was gonna do like 21 and like 29, but they're already taken. Can you zoom in on number 1 and I'll just like explain it?
Okay. So I zoomed in. I zoomed in bigger. Can everybody see it?
I don't know how to move it to like the left. Oh wait.
Is this okay?
Oh wait, I figured it out. Okay. So like the question like starts where it's I kind of wrote down the answer where the question started with negative 21 and then it was 23 minus question mark and then 6 equals negative 25 and then question mark for the 17. So I kind of so all you really do is just like split negative like I kind of just split into the x and y components of the equations and then did like pretty much like negative 21 minus x and then equals negative 25 and then 23 minus 6 equals like question mark or y because those were the two question marks that you were searching for in the answer. And then after solving, you find it's just 4 and 17.
Okay. All right. All right. Anyone has any questions? Okay, Joey has to come back. Oh, Joey is here, right?
No, this is question 1. This is question 1. Someone already did 21. So I didn't really have any others to do.
What about 17? You can explain 17. Adam?
Yeah, I can do 17.
Yeah, let's do 17 as review because I didn't talk about the line representation using vectors.
Okay. I don't have the exact question. 1 second.
Well, let's let me do this. So, because what is a line representation? We have a formula, right? L.
Yeah, it's the x. It's in the textbook. It comes out as x equals it's x1 equals like t and then like the vector. So that's what I did in this example. It gave the tip point -1, -1, -1, and then the two vectors 1, -1, 2, and then you'd also subtract it, or sorry, it didn't give the two vectors. It gave the vector 1, -1, 2, and then you subtract it from the point -1, -1, -1. So that's how I got the equation here.
Okay, so basically let me make up here. So we use vector idea to represent a line in space. So we can, since we have vectors, we can write down representation for any space, a line for any space. So what do we need? We need initial vector. So this one is called initial vector. right? Then what else we need? We need a direction vector. We need two vectors. So this A here is the initial vector. This V here is a direction vector. So if we're given t is variable, because you see this equation is L of t. What is it? It's a vector, right? Because A has a couple of components, V has a couple of components. So L of t is addition of two vectors and will be in a vector. And t is one variable. So this is, so think about the idea of this. This is different from whatever we learned before, right? So here we are dealing with vectors. As someone showed before, we have two representations. We could use initial vector maybe like this, like x1, x. So maybe you have x1, y1, three space. I'm going to use three space because atom is in three space. Initial vector, right? This is the components of A plus direction vector. You know, if you're given 2 points, we subtract those 2 points. We get a direction vector. Depends on which one we treat as the initial point, which one we treat as the end point. So we get another vector, right? Let's call it x, y, z. X, y, z. Then we have a scalar multiplication of t. T is a real value. T is the variable and also a real value. You could think, so you could think this way. Let's see, we have 2 points in space. Doesn't matter which space, right? We have 2 points in space and can be in space, right? Can be in any space. So out of those 2 points, we can always form a line, right? Connecting those 2 points, we always get a line. How do we represent this line in space? So we do this. We pick anyone as the initial vector. Any of these 2 points as initial vector. Then as the initial point or as the initial vector, right? Remember, sometimes we can equalize those two ideas. When we talk about point, we have x, y, z value. When we talk about vector of this point, we think about the line segment with the initial point of the origin. Then, depending on which direction we pick, right? If we pick this one as the initial point, if we pick this one as the initial point, this will be our endpoint. If we use the endpoint, subtract the initial point component-wise, we get a direction. And that would be our direction vector v. Okay. All right, anyone has any question? Okay, Jung E, you're the last one. Then after you, we're going to learn some new material. Just everyone, make sure you don't have a question mark in your head, all right? Anything we talk about, make sure you can do it. If anything confuses you, it's time to ask. Jun Yi, are you ready?
Yeah, I'm sharing it, but it's uploading. I don't know if it's like internet problems or something.
Yeah, sometimes it could be very slow. Yeah, when I was logging on this morning, it was very slow for me.
1 second.
It's coming up.
Oh, okay, I see.
Okay,
So,
yes.
like, I'm presenting like section 1.1 and question 5, that which is asking to sketch the vectors by the giving 2 vectors like the v and w. So I sketched the v as a green line, the point x as 2 and the y as 1, and the w is the red line, like the red segment is 1 and 2. So it asking to sketch also with the addition of 2 vectors. So the purple one, that's what I sketch it for, and I do the addition on the below that, under it, and that's which is the x plus x, and the y plus y, which means like 2 plus 1 and 1 plus 2 equal to like vectors 3 and 3. That's how I did. And also the negation of v, the vector v. So just put the negative sign in front of the x and y and the opposite direction of the v. And also the last one is the black arrows that I do, like v minus w. So it's starting with w and ends with v. So the arrows go towards, like, fall on the point v on the vectors. That's how it is.
Okay, great job. Hold on 1 second. So those are basics, but are very important basics. Let me answer Gabriel's question first. Yes, even sometimes you have a minor errors somewhere else, I still give you credits. But if you're off very much, you won't get credits, all right? So what's missing here? So this question is for everybody, of course, including Zhongyi. Zhongyi, we're talking about when we're in a world of vectors now. Remember, before this class, before this course, we're talking about we're in a world of real numbers, or sometimes maybe complex numbers. But right now, we're in the world of vectors. So what's missing in your picture? Arrows, right? Arrows. So vectors has directions.
Oh, so I'm sorry. I have a question. So like each vectors, I have to put the arrows on the, like, the points that I put?
Yeah, when we draw a picture of it, right?
Oh, okay.
Because it could be two arrows. Because each line segment are two arrows, right? Including which one you're treating as the initial point, which one you're treating as the end point.
Oh,
so
okay.
here we have this V, right? So the initial point will be the origin. Okay, great. Right, vectors, we can add them, right? We add component wise. We can negate them. When we negate, what is a scalar? When we negate, it's a scalar multiplication. So which number we multiply? The scalar is -1. Yeah, -1. All right, great. Okay, good job, guys. Everyone gets credits today. All right. So now it's my turn to talk about, well, unless you have questions. Anyone has questions? 12/16 students have access to edit. Okay, that sounds great. Right, so I'm going to talk about unit vectors. Right. So we know the vector is a line segment. A line segment can be measured, right? Which means it has a magnitude or has a length. So how do we find the length of the vector? Let's see this vector B, right? B is in two space. Half is x value, square root 3/2 is y value. So how do we find the length of B? By Pythagorean theorem in right triangle, right? We do a squared plus b squared, then square root them. So this is for two space. For three space is the same idea. For n space is the same idea. That's how we find the length of the vector. Right? Length of the vector. So in this case, let's see. We just square the first component, square the second component, square the third component, right? Add them up, the square root. Pythagorean theorem. In two space, we only have to apply Pythagorean theorem once. In two space, twice, right? You see here, in three space. So we get, so the xy, so 2 square plus 3 square, we get the hypotenuse of the right triangle. Okay. Then we form another triangle. So we add this, we just get hypotenuse in the third dimension of the triangle. So in two space, we'll apply Pythagorean theorem twice. So in n space, if we want to find the magnitude of the vector or length of the vector, we just apply Pythagorean theorem n-1 times. Basically, we square every component, we add them, and we square root. All right, unit vector means the length is 1. The length is 1. So what do? We just divide every component by its magnitude. So here we see the length of V is half of square root of 53. Right? We just divide every member with half of square root of 3. Right? That's how we get this. If we want to calculate, if we square the first component, we square the second component, we square the third component, we add them up, we square root, we will get 1. So unit vector means length 1. Right? And we use a word for it. We call normalize. Normalization. Normalize. So when we normalize a vector, which means we want to find its unit vector to make a length to be 1, because a lot of times give us a lot of calculation convenience. Okay, distance. So we learned the inner product last time, which is multiply component-wise, then add them, right? Multiply component-wise, we get a number, 3 numbers, we add them, we still get a number. So inner product is a number, right? It's a number. From my previous experience, some students, you know, when I ask for inner product, they still give me a vector. No. Inner product of 2 vectors is a real number. A special case is the length. Right? You see this is A inner product with itself. If we want to find the length of the vector, it's the inner product with itself. It's A dot A square root. To normalize a vector, we use a vector divided by its length or its magnitude. The distance between the endpoints of A and B is, of course, the normalization of subtraction. Right? Let's see this example. We want to find the distance from the endpoint of vector I. What is I? Remember, that's the unit vector on x-axis, which means the first component is 1, the rest components are zeros. And endpoint is vector j. J means the second component is 1, and the rest of components are 0. So we use j minus I. 0 minus 1 square, 1 minus 0 square, 0 minus 0 square, in the end we get square root 2. So the distance between I and j is square root 2. And indeed, if you see the picture of it, right, remember I is a unit vector on x-axis. J is a unit vector on y-axis. Right? Then the hypotenuse, if you want to form a triangle, the hypotenuse, I said, can I write on this? It's very frustrating. Of course, you make a triangle, right? You make a right triangle, you know, one leg is 1, the other leg is 1. So what is the length of hypotenuse? It's square root 2. The angle between 2 vectors. If 2 vectors are not collinear, right? If they are collinear, the angle made between them is 0. So we use this formula, we have this theorem. So A dot B equals the length of A times the length of B and multiply by cosine theta. You could draw the picture to convince yourself. Right? That means we can find an angle made by, usually we say spanned, S-P-A-N, spanned by 2 vectors, right? It's arc cosine of A dot B divided by the multiplication of the length A and length B. It comes from here. Comes from here. So A dot B equals the length of A times the length of B times cosine theta. You You can draw a picture to convince yourself. So this little proof, you're a mathematics major, you should go over this proof. So this is a little example. So we have these vectors, I plus j plus k. What's a component? Okay, if we're given a vector of I plus j plus k, can everyone type in the representation of point wise? Yes, 1, 1, 1. The second one, ijk, point wise representation, 1, 1, negative 1. All right, we should convert this in our head. All right, so vectors can be represented in two ways. We see ijk, that means if we write as a point, there's 1, 1, 1. If we want to write this one, will be 1, 1, negative 1. We do the dot product of these two, right, component-wise. Then when we want to find the angle spanned by these two vectors, we use a formula, a cosine. Then we can consult with our calculators to get an angle. Cauchy-Schwarz inequality. If you're math majored, physics majored, any science majored, this is important for you. Right. So with this single bar, that means absolute value. All right. So because A dot B can be negative. When we dot product of two vectors, the value can be negative. So here, because we want to compare with the length we never measure negatively. All right. So that's why we give absolute value sign of A dot B. We said that the absolute value of A dot B, the absolute value of the inner product of two vectors of A and B is less than or equal to the multiplication of the product of the length. Little proof here. Right. Well, let's just show this one. So vector A is negative 1, 1, 1. Negative B is 3, 0. Because we don't see J here. J doesn't appear. That means J is 0. So 3, 0, 1. Then we do A dot B. So we get a negative 2. Absolute value of negative 2 is 2. Then we find the length of A, which is square root 3. Length of B, square root 10. Multiplication of those two, square root of 30. Square root 30, of course, is greater than 2, right? Because 2 is the square root of 4. If anyone has any questions, feel free to jump in, stop me anytime. Right. When we see something perpendicular to each other, that's for lower dimensions. So we prefer to use another word called orthogonal. Orthogonal. All right. So this is for higher dimensions, right? Orthogonal to each other, which means they form 90 degrees. Orthonormal. Right? Orthonormal. They're mutually, like IJK, they're mutually, and we call it standard basis. Right? We can write any vector in terms of IJK. And because IJK, each one, the length is 1, they're unit vectors. So we call those IJK like a unit normal basis. Right? Unit normal basis, because they are orthogonal to each other. This to show they're orthogonal. Okay, there's one theorem is if two vectors are perpendicular or two vectors are orthogonal, the inner product is 0. Very useful theorem. When the two vectors inner product is 0, that means they form 90 degrees. So let's see this one. So the first vector with component of cosine and sine. The second vector with component of negative sine and cosine. So we do dot product. Dot product of negative cosine sine plus sine cosine. So that's 0. That means those two vectors form 90 degree. The picture is this. Excuse me. So example 7 is saying two vectors, non-zero orthogonal vectors. If C is a vector in the plane spanned by A and B, which means C, excuse me. Think about A plus B, right? Remember when we can add two vectors, right? When we add two vectors, remember the picture is the two vectors form a parallelogram, and when we add them, the longer diagonal of the parallelogram is the addition of the two vectors. So think about this basic case. But for this one, it's saying if C is a vector in plane spanned by A and B, which means C, A, B, C on the same plane, right? And they are scalars alpha and beta, such that C can be written as alpha A plus beta B. I think one of you, when you do representations, when you present, you mention a word called linear combinations, right? So this is also called linear combinations, which means one thing can be written in terms of other things. In this case, C can be written in terms of alpha and beta. No, not alpha and beta. Alpha and beta here is scalars. Okay, scalars. So C can be written, the vector C can be written in terms of vector A and vector B with some scalars alpha and beta here. Right. So A plus B is a special case. In that case, alpha and beta are 1. All right, are 1. So this is a little proof. So you may go over. Another idea is called orthogonal projections. Right. Let's see this figure, the figure 1.210 here. We see V is in a vector. V is in a vector. Right. If sometime we want to get its value on certain axis, we can do something called a projection. So in this case, you see when we project V onto this L, onto this line, so we get this, we get it. So P is basically, P is the orthogonal projection. Orthogonal means 90 degree or perpendicular projection of V on A. So this is vector A. So we're thinking this line can be represented with vector A. So P is a projection of V on A. Anyone has any questions? So at the beginning, this may be a little bit confusing. Actually, we know this stuff. If you think about a triangle, right? If we call a vector A x-axis, then we name another axis y-axis. You see, V is just the hypotenuse in the triangle of P and Q. Right? So one leg is P, one leg is Q. So we call P the projection of V onto x-axis. Then we call Q the projection, specifically orthogonal projection of V on y-axis. So those are special cases. Because usually, you know, we don't have to project on x-axis. We can project a vector onto any line. Any questions? And we have this formula. We can calculate the projection. With a rectangle, of course, if we know two legs, or if we know two sides, we know the third side, right? But we can use vector idea to do the same thing. We can use the vector idea to do the same thing. If we have a vector v, and we take a vector collinear, because P is going to be projected onto A, that means P is on A. P is collinear with A. Right, so this is a nice formula. So we do A dot V divided by the, because A dot V is a value, is a number, real number. The length of A squared, the length of A squared is a number. So A dot V divided by length square of A is a number. Then multiply by vector A. So you see, P is a scalar of A, or A is a scalar of P. Of course, they're collinear. Any questions? So the orthogonal projection of V on A is a vector P. You could use, you could use A as x-axis. You could use A as I, or you could use A as J, A as K, to convince yourself. I heard a sound. Anyone is asking a question or something? Oh, Adam. Oh, Dayeli, question. Dayeli, you can speak.
Yeah, can you just like quickly? Yeah, can you just like quickly repeat what you said about collinear part of the?
Okay. You see here we have vector A. See the figure 1.210. You see vector A here. Yeah. You see vector P here. You see that collinear, right? Collinear means they fall on the same line. Especially typically with vectors, even they're not falling on the same line, if they're parallel, we're still treating them as collinear. Because remember, parallel translation is free when we talk about vectors. So P and A here are collinear. You see the line L? So which means the representation of P and the representation of A are equal. So here talking about we're projecting V onto A or onto the line L. What do we get? We get a vector P. Does that explain? Does that answer your question, Dayeli?
Yeah, thank you.
You're welcome. Great. Keep asking questions. So this is just one example, okay? Triangle inequality, we have this case. So length of A plus B, two vectors, right? The addition of two vectors, the length of the two vectors, remember that's the diagonal formed span, diagonal of the parallelogram spanned by A and B is less than or equal to the length of A plus length of B. Right? So A plus B, you see this is a picture proof. We can parallel translate B to PQ. We see A plus B is just the longer side of A and PQ. Excuse me. All right, then talking about the matrix. Oops. I should go on. So talk a little bit about matrix and cross product. Anyone has any questions about matrix and determinant and the cross product? Okay, matrix is basically we put, matrix is basically made of vectors, right? 2 by 2 matrices, we can look at this is a vector and this is another vector that we call row vectors. Well, we can treat A11, A21 as a vector. That's called column vectors. And A12, A22. Right, you can treat as, we group of vectors together. So this is 2 by 2 matrix. Well, 2 by 2 matrix, 2 by 2 matrix, right? 2 by 2 matrix. And we position them like this. The first one is A11. First row, we read them row wise. A12. Right, if we have third member will be A13. The second row is A21, A22, A23, so on and so forth. The third one will be A31, A32, A33, so on and so forth. Okay, so determinant is defined on 2 by 2 matrix. That's the definition, which is A11 multiplied by A22. We multiply diagonally. We multiply A11 with A22, and subtract A12 is A21. Right. So those are some examples. And how do we multiply? How do we find determinant of 3 by 3 matrix? And we call those square matrix. When the number of row and the number of column are the same, we call square matrices. 2 by 2 is a square matrix, and 3 by 3 is a square matrix. So here we have A11, A12, A13, A21, A22, A23, right? A31, A32, A33. So how do we find a determinant of this? And one of the students, I forgot who, introduced another way. I do not recommend. I think that takes a lot longer time. That's a simple way. Go along with cross product. Remember when we do two vectors, when we do cross product of two vectors, what do we do? Especially in 3 space, we leave I, J, K on top, right? So A11, A12, A13 will be I, J, K, right? Then the calculation of it, the calculation of a 3 by 3 determinant is exactly same as a cross product. But with cross product, we use comma to separate each component because cross product is still a vector. But determinant of a 3 by 3 matrix is a number. So what do? We can work with the first row. We can work with any row we want. But let's now to choose to work with the first row. So what do? We take the first A11 as outside, right? So take A11, work with A11, then we work with A12, then we work with A13. So what do we do? We cross A11 column, we cross the row with A11. So we're left with A22, A23, A32, A33, and we want to find the determinant of these 4 numbers. Or rather, when we talk about matrix, we call them entrances. Right. Then we work with A12. A11, the position is the first row and first column. So 1 position, 1 plus 1 is 2. It's an even number. If it's an even number, it gets to be positive. We work with A12 position, 1 plus 2 is odd. So that introduces a negative sign. Then we do the same. We cross the column with A12. We cross the row with A12. Now we're left with 4 members. A1, A21, A23, A31, A33. Right? We want to find out the determinant of those 4 entrances. Then we work with A13. 1 plus 3 is even number, so gets to be positive. Then we cross the row, contains A13. We cross the column, contains A13. We're left with these 4 members. A22, A21, A22, and A31, A32. We want to find the determinant of those 4 entrances. Determinant is a number, multiplied by a number will be a number. Determinant is a number, so we get 3 numbers. Subtract or add, then we get a number. Okay. So this shows we're working with A12. Right? We can choose to work with any row, right? But here it's just an example of working with the first row. Let's see an example. Let's see the second one. The first one is too small. Okay, this is called the identity matrix. Right? Identity matrix, in the end, its determinant is 1. Determinant is 1, and also we see this is 1, 0, 0. What do we see? Do we see ijk here? 1, 0, 0 is I. 0, 1, 0, j. 0, 0, 1 is k. So determinant of ijk is 1. Let's see this example. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So let's do that. Let's choose to work with the first row. So we take 1, we find a determinant of the rest of 4. We take a 2, negative. Wait, no, take with 3. We do the calculation of determinant 4 times 9 minus 6 times 8. We get -3. No, yeah. 2 times 9 minus 6 times 7. We get -6 times -2, get a positive 12. 4 times 8, subtract 5 times 7. That's -3. -3 times 3, that's -9. We add those 3 numbers up, we get a 0. Determinant can be positive, can be negative, can be 0. And when the determinant is 0, it has a geometric meaning. And when the determinant is not 0, it also has a geometric meaning. So the absolute value of a determinant of a matrix, remember each column, no, each row, we could think as a vector, right? So here we have 3 vectors. Here we have 3 vectors. So the determinant is, if with 3 vectors, they're not collinear, they're not coplane. Coplane means they fall on the same plane. And they will form a 3D object. A 3D object would have volume. So determinant, absolute value of the determinant, is the volume of the 3D object. That strategy is the same as the cofactor of a matrix. Yeah, if you know, if you have learned linear algebra, yes. Yeah. Okay, let's see. So ijk, of course, form a cube. Form a cube with each side length of 1. So 1 times 1 times 1, its volume is 1. With this 3, why it's 0? Because they're coplane. They do not form a 3D object. They only form a 2D object. Because 1, 2, 3, 4, 5, 6, 7, 8, 9, if we pick any row, it can be written as a linear combination of the other 2 vectors. So when the determinant is 0, that means the object formed by the vectors is 1 dimension lower. Here we have 3 vectors in 3 space. But the 3 vectors do not form a 3D object. They only form 2D object, or maybe even 1D object. So that's why it has no volume. That's why its volume is 0. Okay, those are some properties. If we switch the rows, right? If we switch the rows of the matrix, So determinant will be offset by a negative sign. If we switch back, there will be another negative sign. Negative times negative will be positive. If we will switch two in a 3 by 3 matrix, if we switch two rows, that will introduce two negative signs, will be positive. So which means if we switch odd number of rows, we get negative. If we switch even number of rows, we still get positive. Scalar multiplication. If in the same row or in the same column, we have a common factor of it, we can factor out the common factor. All right. Well, and also we see it's the same to put in any other row or any other column. It's the beauty of a matrix. Same thing for 3 by 3. This is to show, remember the matrix 1, 2, 3. That's to prove. That's to prove such matrix has determinant of 0. So this is called a linear combination, right? If one vector can be written in terms of the other two vectors with some scalars, it's called a linear combination, which is saying A is a linear combination of B and C. All right. If one vector is a linear combination of the other two, the determinant is 0. Because why? Because they're collinear, coplane. Because maybe B and C form a plane. Then if A can be written, can be represented in terms of B and C with some scalars, that means A is on the same plane of B and C. With some proofs you may go over. This to show when we calculate the determinants, we can work with any row. Or in the future, if you know more about matrix, you can work with any column. You just pick an easy one to work with. Just, you know, you just have to follow the sign. You have to make the sign right. The sign depends on the position of each entrance. We haven't mentioned the cross product, all right? So A cross B, A is a vector in 3 space, B is a vector in 3 space. A cross B, how do we find it? We put an ijk on top, right? Put ijk on top, because ijk are vectors, and A1, A2, A3, member of A, components of A, B1, B2, B3, components of B. So that is still a vector, right? Still a vector. Determinant is a number times vector. Number, scalar, multiplied by 3 vectors ijk. This is the example of that. Okay, so the first vector is 3, -1, and 1. 3, -1, and 1. The second vector is 1, 2, -1. 1, 2, -1. We will put ijk on top, cross product. Right. All right, so we have 3 kinds of product for vectors: scalar, multiplication, dot product, or inner product, then cross product. Scalar multiplication, we still get a vector back. Dot product is a number. Cross product is still a vector. Determinant is a number. All right. Determinant, sometimes we can write it in this case. It says dot product is A cross B is a vector. Then dot product with the third vector. Right. That's another way of remembering. So this is remembering the determinant of 3 vectors of A, B, and C. Okay, we have another formula. Okay, this is to show, and but sometimes this is useful too. The length of A squared times the length of B squared minus the dot product of those two squared equals to length A squared times the length B squared sine squared. You see, if we square root both sides, right? Well, let's not do that because it's not easy to think about. But basically, this formula sometimes is useful too. So, okay, let me see. Right, this one. So we get A cross B. A cross B is another vector, and this vector is called a normal vector. It's a normal vector perpendicular to A and to B. So this is the picture. We have B vector, we have A vector, so this is called a right-hand rule. Right-hand rule. So we have A vector, we have B vector, and A cross B is this normal vector. So think about A and B span a plane. So this normal vector A cross B is normal to the plane spanned by A and B. Okay, so A cross B is a normal vector. So A cross B, the normal vector, the length of the normal vector equals the product of this vector and the second vector multiplied by sine theta. Multiplied by sine theta. So A cross B, if it's zero vector, if and only if A and B are parallel. Okay, if those two are parallel, the determinant is 0, right? Remember, when we talk about determinant is 0, it's a similar idea. You know, A or B are parallel, or one of them is 0. A cross B equals negative B cross A. So this is different from dot product. But A dot B equals B dot A. But A cross B is negative B cross A. And A cross B plus C, we can distribute. All right. Alpha A cross product with B, alpha can be lived outside of cross multiplication. Okay, these are some examples. Okay, so those two are beautiful. The length of U cross V equals the length of U times the length of V times sine theta. U dot V equals the length of U times the length of V cosine theta. Two beautiful equations. So let's go over this example. This is saying we want to derive an identity, by eliminating theta. So we see clearly, right? Sine theta, cosine theta here. And we want to get rid of to form a relationship only between U and V. So what do? We take the square of the cross product, dot product, right? If we do this calculation, we get this. What's sine square plus cosine square? That's just 1. So look this beautiful equation again. So cross product, so the length of square of U times the length of square of V is the length of the cross product, length of the normal vector squared, plus the dot product of those two squared. Very nice, isn't it? So that's why mathematics is just like a game, right? Just like a game. You make some definitions, you play around with it. Then it may take you very far. If you want to write in this case, right? So you will want to find out the normal vector. Think about this, right? If you want to find the length of the normal vector, one way is to calculate the normal vector, then use the Pythagorean theorem to find it. Well, we could do this. When length of u, length of v, especially sometimes maybe length of u, length of v is given already, and subtract that product squared. Well, this is a beautiful equation. Anyone has any questions so far? Excuse me. Okay, I mentioned a little bit of geometry of determinant. So the absolute value of the determinant is just its volume. Okay, volume in the dimension. Excuse me. And follow some examples. Okay. So geometry of 3 by 3 determinant D is the volume of the parallelepiped. Basically, the object spanned by the 3 vectors, right? So A, B, C, if they're not coplane, collinear, they will form a 3D object. And the absolute value of the determinant of it is the volume of the 3D object. So sorry. And this is a picture of it. We see we have a vector A, vector B, vector C. They're not collinear, they're not coplane. Then they will form, because each two vectors, if they're not collinear, they will form a parallelogram, right? So we have this. We can form 1, 2, 3, 6 parallelograms that form a 3D object. So the absolute value of the determinant is the volume of this 3D object. Again, if A, B, C are collinear or coplane, coplane means they fall on the same plane, and the volume will be 0. There's no volume of 3D to talk about. So the determinant will be 0. And this example shows the volume of these 3 is 11. Okay, you read it. Okay. Now, equations of plane. We talk about equations of line in space. Right? We also use the same idea. But in n space, right, we want to be able to write a beautiful formula to describe, to present a plane. So how do we do it? We use the idea of dot product. Imagine we have 2 vectors. Right? If those 2 vectors, the inner product is 0, what do we say? We say they're orthogonal. So we use that idea. And which vector is guaranteed to be orthogonal to the plane? The normal vector. The normal vector, right? So if we want to write a representation or equation for a plane, what do? We need to find its normal vector. Then we should pick another vector on the plane. Because the normal vector is perpendicular to any vector on the plane. So we just find a vector on the plane and that product with the normal vector. because they form 90 degrees, they are orthogonal, or they are perpendicular. So the inner product is 0. So here we see A, B, C, let's see. So we have this point x naught, y naught, z naught is on the plane P. We have this normal vector with component A, B, C, right? So x, y, z is just any other point on the plane. Right? So we have 2 points. We have x naught, y naught, z naught as a point. We have x, y, z as another point on the plane P. When we subtract those two, we get a vector on the plane. Then we dot product with this normal vector with component A, B, C. So we multiply component-wise, multiply them component-wise, we add them. Right? The short notation is just, we could do n dot, or, well, this is a normal vector dot product with a vector on the plane. Okay, inner product is 0. So what do we need? So to describe, to represent a plane in n space, we need 2 vectors. One vector on a certain plane. Another vector is its normal vector of the plane. All right. Then we do inner product equal to 0. Remember, when we want to present a line, we need also 2 vectors. Initial vector and the direction vector. So here we need the normal vector. Right. Right. So you can write this way. All right. But this is good because this shows you what's exactly going on. All right. It's a dot product of 2 vectors. One is a normal vector, one is a vector on the plane. The picture is this. We want to describe, we want to represent this P with an equation. So we just have to find a vector on the plane. And it's normal, one of the normal vectors. How many normal vectors? There are infinitely many normal vectors. All we have to do is just find one. And ideally, you know, those two share the same initial point. And if they do not share initial point, we can always do parallel translation. Okay, so no problem. So this is one example of it. So you go over yourself, okay? Don't have time to go over myself in class. So make sure you go over yourself before you do your homework. Okay, another one is distance. Distance. So we have a plane, we have a point in the space, and this point is not on the plane. And we want to find the distance of the point to the plane. So what do we do? That's this. Let's just go to this formula. Okay, think about a point in the space not on the plane is x1, y1, z1. And the plane representation is this. And the distance is just this. Okay. This is the next formula. And the picture proof is this one. Picture proof is this one. Okay. This is one of the examples. We have a point in space not on the plane. How do we know not on this plane? We can substitute x, y, z value into this. If it equals 0, that means it's on the plane. If it's not equal to 0, that means it's not on the plane. X is 2, so we have 6. 3x is 6. 2y is 0. Az, negative a. Negative 2, negative a, that's negative 10. Plus 1 is negative 9. Of course, negative 9 is not 0. So we know this point is not on this plane. That means we can find its distance. What do? Just plug into the formula, okay, to get its distance. Anyone has any questions? Okay, so next class, we can present 1.2, 1.3. All right, no more 1.1, unless the question is very interesting. Okay. Otherwise, ideally 1.2, 1.3. All right. So that's for today. And next class, we're going to talk about new coordinates. Okay. Anyone has any questions? My connection is poor. Let me see. My connection is poor. I heard a sound. Did anyone ask something? Okay, the space, right, Muhammad is saying the spreadsheet can be used now. Great, right. You can help each other. All right, Liz. So Liz is in my spring class, right? I'm so happy to see you here. All right, if no more questions, you're free for today. And Adam left early, so I don't know why. He's not going to get full credits for his attendance. All right. Yes, Liz. I'm happy to see you, Liz. All right. Okay, good job, everyone. I see you tomorrow. I see you tomorrow at your evening, my morning. All right, do your homework. Okay, homework is the key. Good morning. Yes, thank you. Good evening. Have a good night. Okay. Thank you. Thank you.
Yeah,
Thank
Professor,
you.
good
See you.